Design of mass detection algorithm using hyper-analytical wavelet transform in digital mammography. Abstract: breast cancer diagnosis and prognosis are two medical applications that pose a great challenge to the researchers in radiology and computer science. Digital mammography plays a vital role for classifying tumors in breast cancer diagnosis. Wavelet transformation is one of the most effective mathematical tools for analyzing the mammograms. The proposed mass detection technique for detection of breast cancer using digital image processing and by using threshold Clahe, which can enhance the image, denoise image based on wavelet transformation. The result of this technique is ensured by the ability of different wavelet transform coefficients, and filtering this coefficients will separate the unnecessary noise and give useful image. These coefficients are then calculated with 2D discrete wavelet transformation for different components, and to compare 2D DWT and hyper-analytical wavelet transformation by using geometric feature extraction with Gabor filter for texture feature extraction in segmentation. Feature texture analysis and automatic ROI, region of interest, using threshold OTSU algorithm for calculating texture measure of mammograms and mass density calculation based on texture measures, and to calculate mass density based on the above features. Application of fuzzy C-means clustering the mass density based on distribution of pixels, and to perform circular transformation in detection of mass shape like round, oval, lobular and irregular shapes, and to train neurofuzzy classifier with mass features in comparison with edge detection algorithm and detect the tumors in an image. 1.1 Introduction. The advancement in biomedical imaging has opened new doors towards recognition of breast cancer by providing quantitative image substitutes. Various imaging modalities and their refinements have encompassed for the utilization of wavelets, leading to methods for quantitatively analyze structural and functional deformities in the breast image assessment. Methods there are based on adaptable computational techniques. The proposed mass detection technique for detection of breast cancer using digital image processing and by using threshold Clahe, which can enhance the image denoises image based on wavelet transformation. The result of this technique is ensured by the ability of different wavelet transform coefficients, and filtering this coefficients will separate the unnecessary noise and give useful image. Calculate with 2D discrete wavelet transform for different components, and to compare 2D DWT and hyper-analytical wavelet transform by using geometric feature extraction with Gabor filter for texture feature extraction in segmentation feature texture analysis and automatic ROI, region of interest, using threshold OTSU algorithm for calculating texture measure of mammograms and mass density calculation based on texture measures, and to calculate mass density based on the above features. Application of fuzzy C-means clustering the mass density based on distribution of pixels, and to perform circular transformation in detection of mass shape, round, oval, lobular and irregular shape, and to train neurofuzzy classifier with mass features in comparison with edge detection algorithm and detect the tumors in an image. Precision mammogram image analysis. Digital mammograms are very useful in detecting microcalcifications to diagnose breast cancer at an early stage. Image processing techniques such as contrast image enhancement, noise removal, segmentation, feature extraction, shape analysis can be done using digital mammograms. The given mammogram image is decomposed into multi-resolution hierarchy of localized information at different spatial frequencies. Multi-scale wavelet representation suggests a mathematical coherent basis not only for existing multi-grid techniques but also for exploiting nonlinear systems. Multi-resolution wavelet analysis provides a natural hierarchy in which the embedded program provides an interactive paradigm for accomplishing scale-space feature analysis. The generalized wavelet transformation algorithms proposed by Ebrahim Jelvefard, Shradhananda 3,5 based on 2D DWT has poor directionality, shift variance, absence of phase information, which is serious drawbacks to make reliable or appropriate tool for the radiologist. The above existing drawbacks of the proposed of novel contribution in hyper-wavelet transformation, HWT, increases better shift variance, good directionality enhancement, and also maintains linear combination of coefficients details of 4-2D DWT subbands, which leads to the development of a reliable tool and help in critical decision making for the radiologist in breast cancer diagnosis. Image pre-processing. Millions of pictures ranging from biomedical images to the image natural surroundings and activities enrich our daily visual experience. It is essential to increase dynamic features in the image to provide qualification images. Image adjustment is usually achieved by contrast enhancement using image histogram measures. Mainly, image enhancement includes intensity and contrast manipulation, noise reduction, background removal, edges sharpening, filtering, etc. The task of mammogram enhancement is to sharpen the edges or boundaries of ROIS, or to increase the contrast between ROIS and background. 1 Balakumaran et al. It is well known that if a region differs in luminance from its surroundings by less than 2%, it is indistinguishable to human eye. Although microcalcifications are brighter than their surroundings, the contrast for some microcalcifications in a dense breast is quite low that cannot be detected by human eyes. The aim of contrast enhancement is to increase the contrast of microcalcifications over the threshold and help identify the minute microcalcifications. The first step in the study of mammogram images image enhancement is denoising the image. The denoising technique should not affect or destroy information content in the image. The removal of background noise while preserving edge information of suspicious area in mammograms is the intended objective. Various enhancement techniques viz. Histogram equalization, neighborhood-based contrast enhancement algorithm, selective median filtering enhancement method based on multi-scale analysis have been done enhancement of contrast of mammogram images. The contrast-limited adaptive histogram equalization, CLAHI, produces images in which the noise content of an image is not enhanced, but in which sufficient contrast is provided for the visualization of structures within the image. Images processed with CLAHI have a more natural appearance and facilitate the comparison of different areas of an image. However, the reduced contrast enhancement of CLAHI may hinder the ability of an observer to detect the presence of some significant grayscale contrast. Threshold CLAHI operates on small regions in the image, called tiles, rather than the entire image. Each tile's contrast is enhanced, so that the histogram of the output region approximately matches the histogram specified by the distribution parameter. The neighboring tiles are then combined using bilinear interpolation to eliminate artificially induced boundaries. The contrast, especially in homogeneous areas, can be limited to avoid amplifying any noise that might be present in the image. Threshold CLAHI method helps in increase of global contrast of an image compared with histogram equalization method. The CLAHI method, being an adaptive algorithm, works for multi-resolution images. Objective: threshold CLAHI technique is applied on original input mammogram to enhance the contrast. Step 1. Threshold CLAHI technique is applied on original input mammogram to improve the contrast. Step 2. Hyper-analytical wavelet transform, HWT, is applied on the output obtained in the first step, then the segmentation at various scales, multi-resolution, to detect microcalcifications and other abnormalities. Step 3, the proposed nonlinear complex diffusion-based unsharp masking and crispening method is applied on the enhanced mammogram. Step 4, the proposed modified threshold CLAHI-based image segmentation is applied on mammograms obtained in Step 3. Threshold calculation maxil equals maximum values. Number underscore bins equals number of histogram bins mu underscore t equals cumulative threshold value. Effectiveness metric of mammogram calculated by m equals maxil slash sum p asterisk 1 number underscore bins dot 2 mu underscore t2. So effectiveness metric may be used, but for large scale processing of mammograms computational complexity may increase. The goal of denoising the image is to use appropriate techniques of refining the images so that the resultant image would have a better visual quality free from aberrations and noises. Noise modeling in images is affected by capturing devices through data transmission media, image quantization, and discrete source of radiation. The characteristics of noise depends on its source. Wavelet transform plays an important role in biomedical image processing. Wavelets first introduced in medical imaging research in 1991 in a journal paper describes an application of wavelet transforms for noise reduction in MRI images. A special issue of IEEE Transactions in Medical Imaging provides a large collection of most recent research work on wavelets in medical image processing. Proposed noise removal algorithm. Calculating features of image. It is challenging process for researchers to eliminate noise from the noisy image to get the original image because it introduces artifacts, blurring, ringing effect, staircase effect and checkerboard effect, in the images. It is very important to identify the noise present in the image to select appropriate denoising algorithm. If the image is corrupted with salt and pepper noise, the filtering methods perform better. The wavelet-based approach is useful if the image corrupted with Gaussian noise. So the denoising algorithm is application dependent. The image denoising algorithms can be broadly classified into spatial domain filtering methods and transform domain filtering methods. Traditional smoothing filters such as mean, median filters are normally employed on spatial domain. Various enhancement techniques, viz., histogram equalization, neighborhood-based contrast enhancement algorithm, selective median filtering enhancement method based on multi-scale analysis etc. may be used for enhancing the contrast of mammogram images. Mammographic image utilizes a narrow range of gray levels, without a well-defined histogram structure. Thus the conventional histogram equalization techniques may not be suitable in enhancing the mammogram images. The wavelet transformations are characterized by two features: the mother wavelet MW and primary resolution PR number iterations. An appealing particularity of the 2D is the interscale dependency of the wavelet coefficients. The main advantage of the implementation of 2D DWT is its flexibility, as it inherits from IDDWT, DOPE-GAS, Simlet, or Koifle family. The main advantage of the classical bilateral filtering method is that it considers both the spatial locality and neighboring points with similar amplitudes at the same time, which make it can better preserving the image edges and textures than the conventional linear filtering algorithms. We propose the adaptive hybrid bilateral filter that smooths the pictures by conserving the edges, suggests a nonlinear combination of close image values. Although bilateral filtering may be a nonlinear technique, it is non-iterative, local, and straightforward. The nonlinearity arises attributes to the nonlinear relationship of picture element values of a picture. Our proposed bilateral filters comprise of two element filters, a domain filter and a variety filter. Domain filter element refers to the normal low-pass filter that provide average values of the image. The implementation of the domain filter utilizes a Gaussian blur kernel for filter weights. This adaptive quality is illustrated within the figures below. Bilateral filter is the resultant product of the domain and vary filters, which ends in an averaging of image pixels supported specially and measures closeness. This is often the central plan underlying the bilateral filtering interpolation technique. Later we apply smoothing process to the pixels that are a unit in shut geometric proximity having similar contents. Thus, it can be assumed to save the average over shut pixels. However, this central plan breaks down at the edges of a picture. During this context, edges ask those points on a picture wherever there are unit discontinuities or sharp contrasts between pixels content and its immediate neighbor. The bilateral filter accounts for the sides by weight pixels supported there. Photometrical similarity additionally to geometric proximity. Proposed adaptive hybrid bilateral filter. The mean square error, MSE, and peak signal to noise ratio, PSNR, are the two metrics used to compare image processing, denoising, quality. The MSE represents the cumulative squared error between the denoised and the original image, whereas PSNR represents a measure of the peak error. The lower the value of MSE, the higher is value of the PSNR. The mean square error, MSE, is calculated by using the following equation 1.1. Adaptive bilateral smooths pictures whereas conserving edges suggests nonlinear combination of close image values. Our proposed bilateral filter comprises of two element filters, a dominant filter and a variety filter. Bilateral filter is the product of domain and a variety filter. It is observed that using adaptive bilateral filter which increases the PSNR value and decreases the MSE.ENL equivalent number of looks. One of the good approach estimating speckle noise levels, is to measure ENL over uniform image region. Larger value of ENL corresponds to better suppression of speckle. The value of ENL also depends on the size of tested region. The wavelet transformations are characterized by two features: the mother wavelet MW and primary resolution PR number iterations. An appealing particularity of the 2D is the interscale dependency of the wavelet coefficients. The main advantage of the implementation of 2D DWT is its flexibility, as it inherits from IDDWT, DOPGAS, Simlet, or Coiflet family. Discrete wavelet transform, DWT, for an image as a 2D signal can be derived from 1D wavelet transform. The easiest way to get the 2D scale and wavelet function is multiplying two 1D functions. The 2D scale function is achieved by multiplying two scale functions as below. Wavelet functions are accomplished by multiplying two wavelet functions or scale and wavelet functions. The implementation of an analysis filter bank for a single level 2D DWT is shown in figure. This structure produces three detailed sub-images, HL, HL, HH, corresponding to three different directional orientations, horizontal, vertical, and diagonal, and a lower resolution sub-image LL. The filter bank structure can be iterated in a similar manner on the LL channel to provide multilevel decomposition. The main disadvantage of 2D DWT are the poor directional selectivity and shift sensitivity. Separable filtering along the rows and columns of the image produces four images at each level. The LH and HL bandpass sub-images can select mainly horizontal and vertical edges respectively, but the HH sub-image components from diagonal features of either orientation. Classification using neurofuzzy. In the field of artificial intelligence, neurofuzzy refers to combinations of artificial neural networks and fuzzy logic. The authors 38, 100, and 16, proposed various methods based on 2D wavelet discrete wavelet transform, which considers horizontal and vertical edges, neglecting diagonal edges, leading to inappropriate diagnosis as it does not take microcalcification which are present in diagonals into consideration. The proposed mass detection algorithm focus on enhancing shift variance and directional selectivity. The enhancement of the directional selectivity of the HWT is made through linear combinations of detail coefficients belonging to each subband of each of the four 2D DWTs. 1.6. Conclusion. The proposed mass detection technique for breast cancer using digital image processing and using threshold Clahe algorithm, which can lead to an enhanced image calculated with 2D DWT for different components, and to compare 2D DWT and HWT using geometric extraction with Gabor filter for texture feature extraction in SFTA, segmentation feature texture analysis, and automatic ROI using OTSU thresholding for calculating texture measure of mammograms, and mass density calculation using the above features. Applying fuzzy C-means clustering in mass density based on distribution of pixels, and to apply circular transform to detect mass shape, and to train neurofuzzy classifier with mass features pave way for fruitful results in the detection of tumors. Comparison to edge detection algorithm. Finally, the experiment results show that the proposed methodology of mass detection algorithm to maintain optimum diagnosis to enhance accuracy improve the poor directionality and selectivity for mass detection. This helps in the early detection of breast cancer that leads to premature control and disclose many possible solutions.